Welcome 2200 activity. We are going to do Faraday's Law and applications together. Well, actually part of it together because a lot of this you get to do on your own or you don't need me. In other words, page 129, part 1, Faraday's Law. You don't need any equipment to do that. You could do that on your own. Page 130, same thing. You could ask you a bunch of questions. It's pretty fun stuff. Just use your brain and you'll be able to figure that out, answer all those questions. Let's see, page 132, actually page 131. That is where we are involved. We need to make a galvanometer. And there's a picture of the equipment we need. I don't have one on hand, so we'll have to simply make it. But as you can see, it's just kind of like household items, right? Wire, magnet. Okay, maybe not everyone has a switch. I'm not going to use a battery. I'll just use a power supply. Let's see, what we need also is a wooden dowel. We need a magnet to hang this on our wooden dowel. The only thing is I want to make something that gives us drastic results, so I'm going to get a more powerful magnet. This magnet we used last time we were together, and it is much stronger, so we're going to have more drastic results when we run a current through this wire. Now this needs to be mounted. If you look at the picture, it looks as though it needs to be mounted in this orientation here, like well, like the diagram shows. This magnet, however, I want to mention, is different from the geometry is different from the magnet that you see in your figure. The north and south poles aren't on these two ends. And I mentioned this last time when we used this magnet. The north and south poles of this magnet are on these two ends. So what does that mean for us? We need to mount this magnet to this rod like this. Let's see, furthermore, if I mount it on the bottom, if there's a torque, it is going to have to fight the torque produced by gravity. So what if I mounted this more like, what if I mounted the axis kind of like through the center of this magnet? That would give us less, that would allow this to move more freely. So we'll go ahead and do that. Now, let's get started and make this so that we can test your predictions and see if they are correct. Okay, hold on. Okay, we were able to knock that out real quick. I want to mention something. So right after I talked about gravity, how we really don't want it interfering with the rotation of our dowel, I kind of misspoke. I realized, oh, wait a minute, we do kind of need gravity, right? We need some natural equilibrium position. In other words, that magnet always ensures that when there's no current through the wire, in its natural position, that pointer is going to be pointed upwards. So what I was going to do is offset the dowel just so that the magnet is slightly below, center of mass is slightly below it. And this would ensure a natural equilibrium position, and then I totally forgot. Anyway, no harm, no foul. I put a rubber band on the dowel. You'll see what I'm talking about. Let's take a closer look at what we made for the sole purpose of convincing you that we have this set up here, identical to this here. By the way, now is the time to pause the video and address this question. On page 131, we did all this work. You want to be able to predict what happens before we actually do it, right? And I mean, this is really testing your knowledge of electricity and magnetism. It should be obvious what is going to happen, so address that question, and then let's test your prediction. Let me put you on pause. So here's a galvanometer. Here is the rubber band I was talking about, and of course that just ensures that we do indeed have an equilibrium position when there's no current going through this. Needle always points up. Also, the poles are labeled. There's the south pole, north is on the other side. Let me convince you that those poles are indeed labeled correctly, and I'll do that by showing you this compass. Now, something is magnetized over there. Right now the magnet is pointed north. When I move it next to our galvanometer, look how it changes. So indeed it feels the strength of the field produced by that magnet and is pointed accordingly. So there we go. Now let me get a picture of your diagram from your worksheet, and what I want to do is convince you that we have this here set up identically. In other words, our coil is wound in such a way that it mimics this one exactly. And you'll notice the battery here, the negative is on the left, positive on the right. We are going to hook this up the same, negative, positive. Without doing like a close-up, you'll just have to trust me that this is identical to that. We already tested the north and south pole of the magnets, and well, you can see how the wires cross there. I crossed them just like they are there. But bottom line is the current is going to flow in the same direction. So let's get this set up and test your prediction. All right, now again, this is to validate your answer. So I close the switch, and there we go. So of course you said it was going to go to the right. Now let me hook up an ammeter to it just for the heck of it. Let me put you on pause. Okay, so I got rid of the switch because I'm going to control the current with the power supply just by messing around with the voltage. What I wanted to say is that right now we've just built a galvanometer. But if we wanted an ammeter, this is all we would do. So I'm turning on the power supply, and I'm increasing the voltage. Now, looking at this ammeter, I see I'm going to adjust it to 3. Let's say I got, okay, 3 amps. What we can do is just make a tick mark here and label it 3. Then I can adjust it up to 4 amps and then make another tick mark here, and so on. So if I calibrate this with this, I have myself a bona fide ammeter. So essentially that's what the difference is. The ammeter actually has readings. It doesn't just detect current like a galvanometer. Okay, we're done with part 2A. Now let's jump into part 2B. Okay, so this is for part 2B. Now, look at the diagram there on page 132 and make sure you fully understand the individual components in the figure there. If you understand what's going on in that figure, then it'll be no problem to understand what you see in front of you here. These here are not conducting supports, obviously. This here is just made of wood. Reason being is that this thing here is very sturdy. You can throw it across the room and it'll still work. The important thing is that there is a copper wire inside those holes. In fact, that is what this is resting on. So there's wire in there, and that wire in there is connected to this lead here. Likewise, the wire on the other side in that hole is connected to this lead. So if I put a potential difference across here and I had a conducting wire across those two metal wires in these holes, then I would have a complete circuit. So this is going to be our electric motor, and I have it hooked up to an ammeter. I'm not using a battery, I'm using a power supply, so we'll be able to knock this out rather quickly. By the way, let's see. Oh, number 1 says examine the leads of the wire coil closely so that you understand which portion of the wire has been stripped of the insulating coating. Let's do a close-up on that. I'll put you on pause. So here's our coil, and what we want to do is examine the ends. So let me go ahead and zoom in on them. You'll notice, first of all, for this end, the insulating coating has been removed entirely. So I'm turning this around and you can see that I took it all off. Now let's look at the other end here. So you could see it has been removed, well, almost, because if I turn it upside down, you could see that I did not remove that portion. So I only removed half. See how if I turn it like 45 degrees, you could see half removed, half not. So not removed, fully removed. All right, let's get this in motion and see what happens. Okay, let's take a look and see what we have set up here. Power supply turned on and connected. There's a potential difference across these two wires that are inside of these holes. Wait a minute, we're connected to an ammeter, but I'm getting no current reading. Well, that's because although the end of the coil, this part, has all of its insulation removed, this side only has half. So the half that is removed is facing the camera. So I'm going to rotate this, and now you can see that the part with the insulation removed has indeed made contact with the wire inside of the hole of this base. So I am indeed getting a current. So when this loop is in any orientation like this, like facing downwards or up, whatever, however you look at it, it is going to conduct electricity. But if I keep rotating it, it is going to get to a certain point. If I move it just a hair, it'll be at that point where the insulation is not removed and I get no current, and it is at that point. See how I can move this, I could rotate this, and there's no current? That is because the this end of the wire has insulation on the bottom end there. Move it this way, insulation removed. So there you go. Now what we're going to do is get a magnet. Let's see if I could do this without blocking the view. I will put the magnet, let's say right here, and I'm going to give this a little spin. Remove the magnet. Put it back. Remove it. And there you go. Okay, what we're going to do now is address 3A and B. So go over this in your manual, answer those questions. By the way, I set that up just exactly like this. In other words, The coil is wound in such a direction that the current would indeed flow in that direction if I hooked up a battery the same way, which I did. So this is identical to this. And I put this kind of sideways like this is here because in part A we are going to rotate the coil clockwise. So they're talking about clockwise looking at this axis. So I'm going to rotate this way. And where's my magnet? According to the diagram, I'm supposed to put north. There you go, north. I marked it so I don't forget. That's south. This is north. I want to put north in the back here. So I'm going to put north behind this and get this rotating, what was it, clockwise? Yes, clockwise. And the question is does this magnetic field speed it up or slow it down? So put me on pause, ponder it, answer that, and get back to me. North, behind the coil. Well, let me get it spinning first. I'll spin it clockwise. So it's pretty obvious what happened. I'll try it again. There you go. Now I will spin it counterclockwise. But you should have already known that. Okay, let's address number 5. So again, if you haven't done so yet, fill that out. Put me on pause and answer that question. So pause. Okay, we're back. Let's validate your conclusion. If you recall, when I put the north side of this magnet on this side of the coil, it accelerated the coil when I spun the coil counterclockwise. So what we're going to do now is reverse these leads north. Now I will spin it counterclockwise. What it did was it stopped it and then it started spinning in the opposite direction. Okay, for part 5, number 2, it says to change the orientation of the poles of this magnet. So instead of north, I'm going to put south. So I'll again spin this counterclockwise. Remember, when I did have north here, it sped it up. But I'm going to put the south pole facing the coil and spin it counterclockwise. So what it did was it stopped it, and then it started spinning in the opposite direction. And just for the hell of it, what we will do is do part 5, 1 and 2 both simultaneous. I'm reversing the leads and I'm reversing the polarity so it's south, and I will spin this counterclockwise. Accelerates it. There you go. Okay, so this is our electric generator. So you've already made your predictions. Let's go to part 2 where we verify them. Now, let me just tell you right off the bat, this is kind of problematic. And the reason being is that I should have picked up a more sensitive microammeter. Now, this is indeed a generator. It's a poor one at that. But I mean, come on. In reality, a generator is going to have like 100 times as much wire as this one here, and it's going to be spinning like super fast. I can only get this spinning so fast before it wants to jump off of those, jump out of the apparatus. In other words, that needle is going to barely move. So let me zoom in on it. Now, what I will do is I'll put this the north pole behind the equipment here, and I'll get that spinning clockwise, and we will see what happens. So I don't know if you could see that, but the needle indeed moved to the left. So I'm going to spin it clockwise again, but instead of the north pole facing the coil, I have the south pole facing the coil. So let's see which direction that needle moves. So it moved to the left. We are indeed generating a current like 1 microammeter. So I'm going to go back to the north pole. I'll put the north pole here, but I'll rotate this in the opposite direction. Now I will rotate it counterclockwise, and let's see what happens. Now remember, when we did it clockwise, the needle moved to the left. Now let's do it counterclockwise. Well, let me get it spinning faster than that. So I indeed, I saw it move to the left. It looked like it moved actually almost 4 microammeters. And again, hope you could pick that up. So that was the north side. I'll get the south pole now behind our coil, and I'll get it spinning counterclockwise. And again, previously when we had the north pole facing the coil, it moved to the right, but I have the south pole facing the coil now, and I'm going to spin this in the opposite direction, in this case counterclockwise. And it moved, the needle moved in the opposite direction. So as I am sure your predictions were all correct, and let me put you on pause. Ladies and gentlemen, that concludes Faraday's laws and applications. As always, it was a pleasure. See you next time.